Before they dominated the modern space industry, the survival of Elon Musk's brand new aerospace company, SpaceX, hung by a thread. In 2006, their operations were confined to the Kwajalein Atoll, a remote strip of coral reef isolated deep in the Pacific Ocean. To keep the company alive, Elon Musk set a singular mandate. They had to build a privately developed liquid-fueled rocket and successfully put it into low Earth orbit. They had to solve the physics of orbital mechanics before their initial funding ran out. A failure to reach orbit meant the permanent end of the company. Their solution was the Falcon 1, a relatively small two-stage expendable launch vehicle. The rocket's lower section, the first stage, was powered by a single pump-fed Merlin engine, burning liquid oxygen and kerosene. After burnout, the upper second stage takes over. It uses a much smaller pressure-fed Kestrel engine, optimized for the vacuum of space. On paper, it was a straightforward layout. This seemingly simple two-stage system concealed a series of complex cascading variables that would trigger 3 successive launch failures. On March 24, 2006, the first Falcon 1 lifted off, carrying a payload called FalconSat-2. This diagram highlights a tiny aluminum B-nut on the main fuel line. Constant exposure to saltwater spray from the tropical launch site had caused hidden corrosion, cracking the nut and springing a leak. The leaking fuel caught fire, spreading across the lower engine compartment. The heat severed the nearby pneumatic pressure lines, resulting in a total loss of vehicle control, just 34 seconds into the flight. Engineers responded by swapping the aluminum hardware for corrosion-resistant stainless steel. They also increased their pre-flight computer diagnostics by a factor of 30. But securing the hardware was only the first step. Fixing the physical plumbing simply allowed the next rocket to fly high enough to encounter an entirely different set of physical laws. Flight 2 launched on March 21, 2007. The first stage performed without issue, pushing the rocket out of the atmosphere and into space. Once in the vacuum of space, the second stage developed an unexpected roll anomaly, exposing a problem with liquids in zero gravity, propellant sloshing. This diagram illustrates the cross-section of the second stage tank. As the vehicle spun, centrifugal force pushed the liquid oxygen outward against the tank walls, pulling it entirely away from the central engine intakes at the bottom. Starved of oxidizer, the Kestrel engine flamed out prematurely. Without that sustained thrust, the rocket lacked the final velocity required to achieve a stable orbit. The engineering solution was to install physical slosh baffles inside the second stage tanks to mechanically restrict fluid movement during flight. With the internal fluid dynamics resolved, the team moved forward with high confidence. They did not realize that a recent engine upgrade was about to trigger a fatal timing error. For the third flight on August 3, 2008, SpaceX introduced the upgraded Merlin 1C engine. This new version utilized a regenerative cooling system to manage the extreme temperatures of launch. The first stage completed its burn exactly as planned, and the flight computer issued the command for main engine cutoff. This diagram shows the difference between the older engine and the new Merlin 1C. Regenerative cooling channels take longer to depressurize, meaning the new engine continued slowly bleeding out residual pressure as a small thrust plume, even after the shutdown command. The flight computer's standard 1.5-second separation timer triggered exactly on schedule. But because the first stage was still producing a tiny amount of thrust, it continued accelerating forward, colliding with the engine bell of the delicate second stage right above it. The fix required no new hardware. They simply adjusted the software to extend the stage separation timer from 1.5 seconds to 5 seconds, allowing the residual thrust to fully dissipate. The rocket was finally physically capable of reaching orbit, yet a microscopic oversight in timing integration had just destroyed their third vehicle and their last scheduled payload. Following the third failure, SpaceX's capital was exhausted. They had under 2 months to build and launch a fourth rocket before going bankrupt. Logistics were accelerated to a frantic pace. Engineers flew replacement parts to Hawaii on private planes and physically repaired a massive dent in the rocket's oxygen tank inside a C-17 cargo aircraft. Since they had lost their commercial payloads on previous attempts, the team rapidly manufactured a 364-pound aluminum dummy mass called PRESat to fly in its place. They bypassed conventional aerospace bureaucracy entirely, prioritizing speed and immediate problem-solving to get this final rocket onto the launch pad. On September 28, 2008, Flight 4 lifted off from Omelek Island. This timeline shows the critical software adjustment. Following first stage burnout, the flight computer held a 5-second gap, waiting for the residual thrust to completely die. The stages separated. The Kestrel engine ignited, and Falcon 1 achieved low Earth orbit, becoming the first privately developed liquid-fueled rocket to do so. SpaceX survived not by avoiding explosions, but by treating failure as an iterative data collection tool. They diagnosed exact anomalies, adapted the hardware, and dared to fly again.